Hello, welcome from EANTC. Welcome to the multi-vendor time synchronization interoperability demo that we have here staging this morning. And the speakers are already eagerly waiting, so I will not waste your time. Just to let you know, we have 12 participating vendors in total, and 9 of these 12 vendors participate in this demo alone. So if you look at the names, which will show up here on the left side in a moment, there is Calnex, Ciena, Cisco, Ericsson, HPE, Keysight, Microchip, Raisecom, and ZTE involved in this very demonstration. So you can imagine it was a massive effort to coordinate it. And thanks very much to all of the involved parties and persons, particularly Jonna from HPE. So I will hand over to you now to talk us through all of the details. Stage is yours.
So, it's, as Carsten said, it's this is one of the biggest topology that we are doing. So when doing the Interop testing in Berlin every year, I've done it now for 7 years. So it's always a great effort to be there. So this year this is our second demonstration, and what we discussed during the testing is not just yesterday we did it together with the SRV6 group. Now it's a kind of a single timing thing, because now we want to showcase a different functions in the timing area. So this is what we call the Class D chain here. As you will see, it's a lot of different boxes here. So we take the different features in the timing that we see being deployed and in use in the live networks. So full timing support, which is a lot, much deployed with the 5G. So we kind of split this chain up here that I will go through here. So on the left side here, with the red one, we have actually 4 Class D boundary clocks. There we're running the full timing support with the G8275.1 in hybrid with enhanced sync. So actually, we do the enhanced TLV on the sync side to get even more precise synchronization signal, but enhanced sync, the quality level, and things there actually gives another information set that you can really look on the different hops. You can see the organized clock ID, which you don't see with the regular ESMC. So that's the 4 nodes here. And then we are adding a partial timing support, which is shown in green here. And you see the Ericsson device is being used as the interworking function from the full timing support to the partial timing support, with use of the G8275.2 profile, which does run over either IPv4 or IPv6 routed network here. So it doesn't need to have all the boundary clock in a chain to support it. Of course, you can do that with .2 as well, but the whole thing, if you have an unaware full timing support network, and you want to as well sync them, you want to use the .2. On the nodes, the dot on the Ericsson node, that is actually looking back to the GM, the TP4500 for Microchip, over routing network through the boundary clock in the full timing. So that has .2 session directly there. So the nodes in the chain is not aware of that. And then into the SETI is also .2, and then we have the Ignite from Calnex that Neil will talk about, but that introduced some asymmetry here. And then we come to the Ciena, which is working for as an APTS node, assisted partial timing support, which is currently connecting to GNSS, and as well does the interworking function now, but now from the partial timing support to the full timing support that are the chain here we have on the right side here. So down here, we are doing the interworking function. To the .1, we have, again, 4 Class D boundary clocks, but now we are running regular sync because not all the nodes there are supporting the enhanced sync here. So that's the chain. It's a lot of devices. And on top of that, we are adding a second grandmaster for Microchip to really simulate dual grandmaster, dual timing sources. And this was also connecting to some of the devices to really demonstrating the passive port monitoring features, that we can do measurement on the offset between the 2 ports to have a notion about the performance on the boundary clock. Because you typically don't see the performance on the boundary clock when you, on the regular CLI, you need a test equipment, and we have a lot of them here. So we have the notion here with that. So that you'll see on the bottom, you have a different test equipment from both Calnex, the Neo, and as well the TSA from Keysight here. So we have connected them into the different nodes to really show the performance individually on the node, but as well what Neil will show here, the end-to-end performance here. So this is actually what we did. So I explained this already, that we have the full timing, the partial timing support here, the redundancies, the asymmetry compensation, the full timing here. But what we as well did this year, and this was actually a thing we have been testing for some years, is that we have Interop testing doing PTP over MACsec between the HP and the Cisco device there. So between those two nodes there, we are running MACsec on the whole port, and we are running both PTP and Sync over there. So with that, I will leave it over to Neil to show you the end-to-end results there for the measurement here.
Good. Thanks, Bjornar. So yeah, as Bjornar has explained, we have multiple different technologies applied in our network today. So what we're looking at here is the end-to-end time error performance, the accumulation of time error across these nodes, across these different technologies. Our orange at the top here is measured directly from our first node. Something's happened here. We've now got a large offset. So we should not be seeing 600 nanoseconds, and we weren't before this demo actually started. So something's happened, but what we can see is we have stable time transfer through the network, and we can look at that in terms of the various limits that are defined to define network performance. So we can see here we've got a very tight wander mask, traceable to an EPRC, which is what our Microchip device is performing as today. And we're well within the limits, despite the fact we have these different functionalities, these different capabilities in the network. We're actually running two separate segments at the moment. As Bjornar mentioned, we have an APTS device that's currently locked to GNSS, and we can see the difference between the two scenarios where we're looking at full timing support direct compared to APTS across an extended network. We can look at that in terms of our relative time error, so we can see there's quite a bit of variation going on there. This was one of our last-minute panics we had. This is all tied to GNSS. GNSS, as a reference, takes time. We didn't have time. This is the result. But what we can see is everything's working together. We are gaining stability. We are transferring time, despite all these new technologies that we've actually put into our setup here. And this one has now crashed. So what we can also do is look at our PTP in terms of protocol in order to understand, are we actually seeing what we expect? Might be a little bit small, but we can see here we're getting clock class 6 at both ends of the network. We have locked chains here. So what I'm going to do now is hand over to Rob, who's going to look at the APTS node, currently locked to GNSS. We're going to switch from GNSS. We haven't tried this yet, so we're setting him up for failure, but I hope he's going to succeed. Rob.
Thanks, Neil. Good morning, everyone. Let me just jump across here to the SS. Here we are. And we are up the top here. Okay, so we built this. It's a live demo, lots of gremlins this morning, but what you can see is the way we are connected. So here you see the GNS global values. We are connected up, detected, and you can also see that we are picking up a bunch of satellites from up top there. So when you look at the way we are set up for the protection, we have the phase protection group here, so you can see that we are locked onto the GNSS. And then we see down the bottom here of the screen, you have the PTP in that _30, which is port 30 on our box. And you can see that it's got an offset. So being a live demo, what we will do is we will switch and actually pull the cable. So you know this is going to be a real demo. We're not slide decking this at all. So let us, I think, just break it and see what happens, because we've been up, as you can see, this morning for about 37 minutes. Not typically long enough for a proper sync demo, but let's find out what we do. So here's our antenna. disconnected, and let's see what we've done. So straight away, you can see there's a difference in the outputs here. We are now offset, and we have switched. Let's hand it back to Neil and see what we are measuring on the test set, because I think that is where we'll see a lot more information than just what we're going to see from CLI.
What we can see now is we haven't yet got any effect on the time error, but we can see here our clock class has changed, because when we've switched reference, we've gone into holdover on that downstream chain. So we can't see the effect on time at the moment. We're running through a timeout process, basically, which is why the top two graphs aren't updating. But you can see here that we've understood something has happened in the network. The devices have now gone into holdover mode. And eventually, when Rob starts presenting our corrected PTP through the APTS network, then we will see the step happen at the end of the chain on the pink line. So we'll leave that running. If you're interested, come back in 10, 15 minutes and we'll see what's actually happened. Hopefully, we would see that step. But this shows that what we can have is these multiple technologies running together. We have the ability to interoperate correctly. We can get acceptable performance as per our network standards, and we can ensure that these devices are interoperating to meet the requirements of that end application, which is our 5G network. I think that's us done for...
As you see, it takes some time to stabilize to the GNSS, but if you really are interested into the results, we did this test case, and it's described in the EANTC test report that you find on the EANTC website. So go on there, because there we have the time, we have the real GNSS there, and here we are simulating. So, but it shows the behavior here, and it shows a lot of different technology that we are using into the network here. So I think we conclude with that, and thanks for showing up here.
Thank you very much, all.